Welcome to chapter 10. We're going to be talking about work and energy, and those are pretty big ideas. And actually, this first section is going to be fairly long, so I'm not going to spend a lot of time on each portion. Try and keep up with me as I move through this fairly quickly, but I don't want to waste your time, obviously. I do want to mention though, this launch lab could be really interesting to try out. You can do it with sand, as it says, or you can try it with maybe baking soda or sugar or something like that if you don't have sand. And any kind of object you want to drop will be useful for it, but try it out. Okay, in this section, there are a lot of vocabulary terms, so you want to pay close attention to those. I will spend a little time on that in this. First off, the book gets into a little derivation. You see down here where it says FD is equal to 1/2 MVF squared and minus 1/2 MVI squared. That's a derivation of what we're going to come to find is called the work energy theorem. And this is a very useful theorem. It's very similar, by the way, to what we've already seen as the impulse momentum theorem, right? Remember, if impulse momentum was F times t, right? The force times the time is equal to the change in momentum. Well, this is going to be F times d, which is what we are going to define work as. And it's going to say that work is equal to the change in energy. Okay, change in energy, specifically in this case, change in kinetic energy. 1/2 mv squared is kinetic energy, which you've probably seen before in other science classes. There is one weird wrinkle in this little equation here. When you talk about multiplying force times displacement, you've got two vectors there. And it turns out that when you multiply a vector times another vector, you have to consider some things that you normally wouldn't have to consider. You have to consider what direction they are both going in and what the direction is relative to one another. I'll show you what I mean in a second. Okay, you see one of those vocabulary terms there, work, is force times displacement. You can see the units for work are the joule, okay, and that is, by the way, also the unit for energy. Okay, the joule is the unit for both of those things, work and for energy. To give you an idea, it says it's about the amount of energy that it takes to lift an apple 1 meter. Okay, if that helps you, that's nice. But it does kind of tell you that a joule is not very much energy. It's not very much. Now, I mentioned that angle matters in the multiplication of force times displacement, right? Here's how that goes. Well, if you were to push on a car like this picture shows, right? And you're pushing it forward, but you're also kind of pushing downward, right? Well, it turns out that you pushing downward doesn't actually help in causing the car to get faster, right? I mean, that makes sense. If I was to push down on the car hood, the car wouldn't be moving side to side. So that's not helpful. That's not going to cause a change in its energy, really, in fact. And so the only part that matters is the horizontal component of your force. And so that's why you have to actually add in a cosine of theta term. Okay, so when you look at the equation on the right there, it says work is equal to FD cos theta, theta being the angle between the displacement, right, in this case forward, and the force, which is slightly angled downward, right, 25 degrees downward. Okay, so you need that cosine of theta term in there, technically. This also means, by the way, that if I were to, let's say I was to move across a room holding something in my hand, right? If I was to move across a room holding something vertically in my hand, pushing it upward, the force pushing it upward is not really having a work type effect on the object. And so I'm really, my hand pushing up is not doing any work on that object, technically. So that's kind of weird. All right, might want to take note of that. Okay, here's one little wrinkle here, and that's that when a force changes over some span of time, or on a span of distance. In particular, this matters when you're talking about springs. So, like if you compress a spring, right, when you first push on a spring, it's fairly easy to push on, right? It doesn't require a lot of force. But then eventually that spring, as it starts to get really compressed, it starts to kind of harden and it makes it more difficult to push on, right? So the force of a spring actually varies based on how compressed it is. Well, in a case like this, the work done by the spring is actually going to depend on that changing force, right? So, what can you do in this case? How could you determine the work of that spring? Well, you would use a graph. You would actually use a graph, and very similar to what we did with velocity versus time graphs. If you remember, we used velocity versus time graphs and took the area under the curve to find the displacement. Well, with a force displacement graph, you can use the area under the curve to find the work. Okay, so it's sort of the same idea. Here, I'm not going to go through these, but please do read through these problem-solving strategies. They're very useful. And then, of course, do some of these problems. You'll find them very helpful. Okay, now we finally get the term energy. Okay, I've talked about it plenty already, but energy is the ability of a system to produce some change, right? It might change the position of something, it might change the speed of something, but some change like that, the thing that allows an object to do that is called energy. And there is a relationship between work and energy, which we talked about earlier, which we call the work-energy theorem, right? And I showed you another way to show that that actually sort of breaks things apart, right? F times D is equal to 1/2 mv squared minus 1/2 mv squared, earlier in the chapter. Now that 1/2 mv squared that you saw there, again, we call that the kinetic energy as opposed to like potential energy. Those are two different kinds of things, right? Kinetic energy is motion energy, and potential energy is positional energy, right? There you can even break apart kinetic energy even further. There's different kinds of kinetic energy out there. There's kinetic energy moving from side to side, right? That's called translational kinetic energy. But there's also rotational kinetic energy, right? If something is spinning, it has energy. It has the ability to do things. Like if you take a ball and you spin it and you drop it on the ground, you know that that ball doesn't come straight back up. It also goes to the side. Well, that's because of its rotational kinetic energy. Anyway, but translational kinetic energy is the 1/2 mv squared kind, right? That's the one you're probably most familiar with. All right, the last term in this unit, or this chapter, I should say, that you need to really look at is power. Okay, power is change in energy divided by time. All right, so delta E over T, or because we know that work and change in energy are equal to each other, it's also work over time. So power is work over time. And you kind of understand what power is, I think, right? You know that like my car, which goes from 0 to 60 in 8 seconds, is very different in power from a Tesla or something, right? Which goes from 0 to 60 in 2 seconds, right? Very different. Horsepower is the term we often throw in there, right? Well, that's a kind of unit for power. The more common unit that we use in science for power, though, is the watt, W-A-T-T. And 1 watt is a joule per second. It's a joule per second. Now, it's not a lot of energy per second, and so we often talk about things in kilowatts, right? You might be familiar with that from like your light bulbs, kilowatts and all that. Okay. Let's see what's left. The book also does talk about a relationship between power and speed, which is quite interesting. You might want to check that out. And try these questions at the end. Let me also mention that section 2, we're not going to really talk about right now, but you might find it really interesting. Machines are very interesting, and the ability to do things with machines that you couldn't otherwise do is very useful. Okay.